We are starting chapter 7 today. So we're all done with previous ones. Note that we skipped chapter 5, so we'll come back to that one later, talking about nuclear chemistry. But today we're going to go on to chapter 7. This is kind of the last math-heavy chapter of the year, or of the semester. So we're going to talk about some calculations regarding molecules and how we determine the amounts of molecules, that kind of stuff. A little dry, but the good news is once you figure that out, it's always pretty much the same. So when you can do that, it's going to take a little work, a little practice, but I think you'll be all right. So, okay, let's talk about it.
Yeah,
Have you ever heard of the mole
yeah.
as a chemical concept?
Stupid.
It's stupid. Sorry.
No. It makes me mad.
It makes you mad? Okay. Anybody else? Any other anger about moles? Just neutral feelings about them? Well, it's nothing to get too upset about. A mole is just a number. And it's a particular number. It's a very, very large number, but it's not something special about it in terms of, it's not a measurement. It's just this number. It's a number that refers to a quantity. And the number is really, really big. 6.02 times 10 to the 23rd. It's a number that's so big that you really can't express it without scientific notation because it would be ridiculous. But let's try it. So that is 602 that number. I think that's right. Let's count it out and see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I think that's right. So, yeah, big number, right? I don't even know how you would say that.
I think it's octillion.
Is it octillion? So you got million, billion, trillion. What comes after trillion?
A lot.
Quadrillion?
Yeah.
Pentillion? Sextillion? Septillion? So 602 septillion?
Yeah.
All right, anyway, big number. So we always express it in scientific notation because we don't want to write that many zeros all the time. But it is just a big number. It doesn't refer to any specific thing. It's just a number. We say that that many of something is a mole of something. What are some other words that we know about, or what some other numbers that have words associated with them, that have names for that particular quantity? Think of any? We're just talking about donuts. How many donuts do you get in a box? And how many is that? 12. 75. Sometimes, yeah. That's the same thing. A dozen is 12 of something. It doesn't tell you what it is. It just is 12 of something. It's a quantity. Yes, but that is a specific quantity. That's telling us how fast light is going. It only refers to that same thing, and it has a unit, which is meters per second in that number. This is just a number. Dozen is just a number.
Light year.
Oh yeah, so a light year. But again, that's a distance, right? It's the distance that light travels through the air. This doesn't have a unit. Dozen doesn't have a unit. You put whatever you want, you're counting as the unit. So you can have a dozen donuts, and then donuts are the unit. You can have a dozen apples, and apples are the unit, whatever. So as you could count numbers, 1, 2, 3, 4, 5, whatever, you can count by dozens. You could say 1 dozen, 2 dozen, 3 dozen, 4 dozen, and that half a dozen, 0.268 dozen, and that tells you it's some fraction of 12. So you would multiply however many dozen by 12, and you'd have that. What are some other numbers that we have words for like this? You think of any others? Oh, yes, that is a number with a name, but it usually doesn't refer to a quantity. So yeah, that fits. But what about as a quantity? There's not that many of them, but we could have like a, well, there's Baker's dozen. You ever heard of that? What's that? It's 13,
Oh, damn.
which I don't know why. Hold on, my cursor's going crazy here. Whoa, what's happening? Did you see that?
Yeah.
What is happening here? Is someone else controlling my thing? Let's try that again. Baker's dozen is 13. I don't know where that, somebody in my other class said that means that's because the baker makes one for himself. Herself. I've also heard that it's like, if you buy a dozen, you get one free. So that's like a baker's dozen. Who knows? But anyway, we have that word. Another one, if you're in shipping or anything like that, you might have heard of a gross. Do I know how many is in a gross? It's a bigger number. It's 144, which is 12 dozen, a dozen. So it's a 12 squared. Like pencils, if you have a box of pencils, is usually a dozen pencils, and then you get a big box, like a case of pencils is a gross, and that's 12 boxes of 12, something like that. So anyway, some different words. And the reason we put those in there is that I want you to think of a mole in these terms. Oatmeal. It is the same idea. It is a word given to a particular number, and that number can be of anything. It doesn't refer to a specific quantity of something. It's just a quantity of whatever. Now, the reason that we have that number, that enormous number, it would be certainly ridiculous to think of anything on our usual day-to-day scale in terms of a mole of those things. We wouldn't have a mole of donuts, probably, right? Probably isn't enough. I mean, it's just unimaginably large. Like there isn't enough flour in the world to make that many donuts. You know, it would something that many donuts. I saw a thing about it. You know, that many donuts would like cover the earth to a distance of like 5 miles or something. I don't know. Anyway, it's a huge number. So that number is only useful if we're talking about things that are super, super, super small. Because anything on a scale that we can kind of imagine is just a quantity that size would be just too many. So you can't even deal with that. So what do you think we're going to use it to count that's very small? Yeah, atoms. So this is a number that helps get us from the tiny realm of atoms and molecules where we can't see anything, we can't count anything, to the realm that we can actually deal with. So if you have 6.02 times 10 to the 23rd atoms, you have like a small handful, basically, of stuff. Where that number actually comes from is that 1 mole of carbon atoms, so that's 6.02 times 10 to the 23rd carbon atoms, weighs 12.011 grams. So do you see what I mean about translating from the atomic realm to the physical realm? We can't count individual carbon atoms, but if we have 12.011 grams of carbon, which is like about a handful, small handful, then we know we have that many carbon atoms. All right. The way we use this in the lab, anybody recognize that number, by the way, 12.011? Where have you seen it before? Yeah, that's the number in red that's under carbon. So pretty soon we're gonna talk about how these numbers are molar masses to help us count these things. All right, has anybody, someone's taking control of my computer again. It's kind of freaking me out. Maybe the mouse is just malfunctioning or something. Has anybody ever seen the thing where like you go to a candy store or something and they have a giant barrel of jelly beans and you have to guess how many jelly beans are in there, and then if you guess closest, you win all the jelly beans? You know, have you seen something similar to this? Maybe not jelly beans, maybe, I don't know, whatever. If you haven't, imagine this happening. You see this giant thing of jelly beans. It's like a huge bucket, and it says, guess how many jelly beans are in the bucket. People put in all their guesses, and whoever's closest wins all the jelly beans. So how do you think they figure that out? Do you think they pay somebody to count every jelly bean and determine how many are in there? So how do they figure it out? By weight. So how does that work? Yeah, right. So you'd weigh one jelly bean. You'd assume all the jelly beans are about the same weight. You'd weigh one jelly bean. Then you weigh all the jelly beans, and you divide. You see how many jelly beans there are. Right? That's how we count atoms. We can't count individual atoms. We can't have some tiny little tweezers and pick out atoms and count them. It would take a really long time. But we can figure out how many atoms we have by knowing how much one of them weighs, and then weighing all of them, and then dividing. And that's exactly what we do. Now, because there are so many atoms in any given sample, because atoms are so small, instead of counting them one by one, we usually count them mole by mole. So rather than saying 1 carbon atom, 2 carbon atoms, 3 carbon atoms, we say a mole of carbon atoms, 2 moles of carbon atoms, 3 moles of carbon atoms, where each mole has that large number of carbon atoms in there. All right, so we can say things like, how many carbon atoms are in 0.50 moles of carbon. Actually, wait, hold on. Not moles, grams. How many carbon atoms are in half a gram of carbon? We can weigh half a gram of carbon. Carbon's a kind of a black powder. You can go up to the lab, put your thing on the balance, weigh out half a gram of carbon. No problem. That's not too difficult. But we can actually, using this idea, we can figure out how many carbon atoms are in that sample that you've weighed out. This quantity here, this idea, is called the molar mass. And so the molar mass of carbon, also known as the atomic mass or the molecular weight, tells us how much mass is in a mole of a given substance. And we look that up on the periodic table in those red numbers underneath there. So the molar mass of carbon is 12.011 grams per 1 mole. The abbreviation for mole, by the way, is MOL. It's not much of an abbreviation, but you save a letter, I guess. M is meters, MO is months, so that was the best we could do. But that's the abbreviation. So we're saying that the molar mass of carbon is 12.011 grams in each mole. If we have 0.5 grams, we can use this like a conversion factor to solve for how many moles we have, and then subsequently how many atoms we have. So let me show you what that looks like. If we have 0.50 grams of carbon, we can multiply that by a quantity that converts grams of carbon to moles of carbon. That quantity is the molar mass, what we just talked about. So we have to make sure the units line up properly. It's 12.011 grams per 1 mole. Then we can also know how many atoms are in a mole of carbon, because we know how many of anything is in a mole, which is, yeah, 6.02 times 10 to the 23rd. That's how many of anything is in 1 mole of that thing. So we do that calculation, 0.5 divided by 12.011 times 6.02 times 10 to the 23rd, point 0.25 times 10 to the 23rd atoms of carbon in half a mole, or in a, sorry, in half a gram. Now, a note on scientific notation. For this class, if you want to leave scientific notation in that form, that's fine. I don't have a problem with that at all. Official scientific notation, you always have one non-zero digit for the decimal place. So for proper scientific notation, you're supposed to move this over and call this 2.5 times 10 to the 22 instead of 0.25 times 10 to the 23rd. Again, in this class, I don't care, so you don't have to worry about it. If you go on and you need to do stuff with scientific notation, realize that it's not quite right to say 0.25 times 10 to the 23rd. All right. So we've got how many carbon atoms are in a certain number of grams of carbon. What if, can we also answer this type of a question? How many water molecules are in 8 grams of water? Same basic question. But now we're looking at a whole molecule instead of just an atom. So how do you think we figure out the molar mass of a whole molecule?
You add the masses again.
Yeah, you add the masses together. So the molar mass of water is going to be the mass of 2 hydrogens and an oxygen all together. That's going to be 1.0 plus 1.0 plus 16, which is 18 grams per mole. How you pick when to round these things, again, as with anything else in this class, it's kind of just up to you. If you want to just round them to whole numbers, that's okay. If you want to use a decimal place or two, we didn't talk about the official rules for doing that, so however you want to do that is fine. Molar mass of water is 18 grams per mole, and we set this thing up the same way. Eight grams of water, and then we're going to convert grams of water to moles of water using that molar mass, 18 grams per mole. Now notice our last term there, same number, but now it's a measure of molecules per mole because the question is, how many molecules are we talking about? So that number doesn't have a unit. That mole number, which the official name for that is Avogadro's number, doesn't have a unit. Its unit is whatever you're trying to count. So whatever you're trying to count, it's that many of those things. So calculate this one out too. 8 divided by 18 times 6.02 would be 2.7 times 10 to the 23rd. Molecules of water. Yep.
How did you get the 16? How did you get the 16?
Yeah, good question. These are the molar masses of the individual atoms. So hydrogen is 1 and oxygen is 16. We get that from the periodic table from the numbers on the bottom. You add them all together because water is H2O, and that's how you get that molar mass. So what if we asked a related question here? how many hydrogen atoms in this sample? When we figured out how many water molecules there are, how many hydrogen atoms would there be in that same sample? How did you figure that out?
Just add the hydrogens together and just subtract the oxygen.
Not exactly, because our quantity is still given in grams of water altogether.
Equations and then subtract them.
Not even that. I think it's even simpler than what you're thinking of. We look at the water molecule. How many hydrogen atoms are there in one molecule? So how many hydrogen atoms are there in a mole of water molecules? 2 moles, right? If there's 2 hydrogen atoms in one molecule, then there's 2 moles of hydrogen atoms in 1 mole of water molecules. Do you see how that would work? Because this is just a count. This is just a way of counting things. If this gets confusing in your head, go back to dozens, because we're more used to dozens. So if you had a dozen water molecules, how many hydrogen atoms would you have? Or you have a dozen water molecules.
24.
24. You see why? There's 2 hydrogens per molecule. So you're always going to have twice as many hydrogen atoms as you have water molecules. So it's the same thing here. If we have 2.7 times 10 to the 23rd water molecules, we can say that there are 2 hydrogen atoms per each one water molecule. Multiply that by 2, we've got 5.4 times 10 to the 23rd hydrogen atoms. All right. Now, normally when we do these types of calculations, the reason that we care about this, the reason that we want to do this, is because of the next part we're going to talk about, which is chemical equations. When we do a chemical reaction, when we talk about molecules reacting with each other, we're talking about counting molecules. We're saying one of these reacts with one of these, or 2 of these react with 2 of these, and you put them together and then they form one of these. Those are all counting type situations. The mole thing allows us to count those molecules. Just like the jelly beans, they're too small to count individually. So we can weigh them, we can use moles, and then we can have a count of how many of these we need for how many of these. So let's talk about chemical equations, and then we'll come back to these moles and how we use them in calculating those chemical equations. Notice I said chemical equations and not chemical reactions. A chemical equation is a way of expressing a chemical reaction on paper. Chemical reaction is the thing that actually happens, the thing like what we've been doing in lab. The equation is how you write what happens on paper. So let's look at an example here. Hydrogen gas and oxygen gas react. Anybody know what they produce when they react? Water, yep. Few things to note about this. This is called a chemical equation. This is how we show what chemical reaction happened. There's this big arrow in the middle. And as you can probably tell, that means that we start on one side and we go to the other side. The stuff that we start with are usually called the reactants, or reagents, or starting materials. And the stuff that we end up with is the product or products. So the equation shows us what the reactants are and what the products are. Other things that you'll note in the formulas here, there's often a little letter in parentheses after the chemical formula. What do you think that refers to?
State.
Yeah, that's the state. G is for gas. L is for liquid. S is for solid. And then there's one more, AQ, which isn't exactly a state, but it stands for, yeah, aqueous, which means dissolved in water. So if you saw an equation that said NaCl with a little s next to it, you know it's talking about powdered salt, powdered sodium chloride, like you get in a jar or something, or in a salt shaker. If it says NaCl AQ, that's talking about a solution of sodium chloride, so salt water, salt dissolved in water. So it tells you something about the state. In this case, we have all gases reacting and forming water vapor at the end. Okay, there is one problem with this reaction that we have, or with this equation that we have not addressed. Does anybody see a problem?
There was 2 hydrogen and 2 oxygen, and in the product without any oxygen.
Yeah, that's a big problem. Did everybody see that? On the left side in our reactants, we start with 2 atoms of hydrogen and 2 atoms of oxygen. But on the right side, we only have 2 atoms of hydrogen and 1 atom of oxygen. So according to what we've written here, a hydrogen molecule reacts with an oxygen molecule, forms a water molecule, and an oxygen atom simply ceases to exist, disappears. That is not chemistry, that is magic, and that doesn't happen. So that doesn't work. Oxygen can't just disappear. There is something called the law of conservation of mass, which says that in a chemical reaction, matter can't be created or destroyed. We can't magically create matter out of nothing, and we can't magically destroy matter into nothingness. Now, there's some exceptions to that when we get into nuclear chemistry, but in basic chemical reactions, that holds. So what's the problem here? How do we fix that? Does that mean that this reaction doesn't happen?
In the product, we need to move this 2 into the front, so before the H. So then there's going to be 2 hydrogen and 2 oxygen. Can we do this?
Not quite, because we're talking about a different compound then. So another way of thinking about that is, what if instead of H2O, what if we wrote that product as H2O2? Would that work? I mean, it would work from the mass side, right? Nothing's disappearing then. But what's the problem? We didn't. But why would we, if we said, okay, there's a problem here, so maybe instead of H2O, this product should be H2O2. Is that the same thing as water?
No.
No. Does anybody know what that is? Yeah, that's hydrogen peroxide. Is that the same as water? No, don't drink hydrogen peroxide. Yeah, totally different compound, right? It's what you use to disinfect wounds and bleach your hair and stuff like that. Not water, not water. So when we change those little subscript numbers, we change the identity of the compound. We change what we're talking about. So we can't change those little numbers. Similarly, if we took that 2 out and put it out like you were talking about in front, and we made HO instead of H2O, what's HO? It's actually an ion. Hydroxide, yeah. Is hydroxide the same as water? No. So we can't change those little numbers below. Those are our compounds, and they have to stay compounds, and we can't mess with them. So that's not going to work. The way that we make this work is really what this is telling us is that this is not the correct ratio that these reactants react in. In other words, 1 hydrogen molecule doesn't react with 1 oxygen molecule to form 1 water molecule. they react in a different ratio, 2 to 1 or 3 to 1 or 6 to 3 or whatever. In this case, it's 2 to 1. If we have, instead of one hydrogen molecule, we have two of them, and we react that with the oxygen molecule, we can form two water molecules. And now we don't have that problem anymore. We've got 4 hydrogen atoms on the left and 4 on the right. We've got 2 oxygen atoms on the left and 2 oxygen atoms on the right. So it all works. All right. To express this in the actual equation itself, we put numbers out in front of each reagent telling us how many of them we need for this ratio. So we would say this should be 2 hydrogens and 1 oxygen forms 2 water molecules. Since there's no number next to the oxygen, we assume it's 1. But that now accurately expresses what's really going on, that you need 2 of the hydrogen molecules to react with 1 of the oxygens. And this is what we would call a balanced chemical equation. So we brought it into balance now. And now we don't have that problem of magically losing or gaining masses. All right, so that was kind of the conceptual overview of why we need to do this. There's also kind of a mechanical, practice-based part of just how do you balance this chemical equation? How do you go about making sure that your equation that you write down is always balanced? So that's what we're going to look at next. Here's an equation for this iron-sulfur compound reacting with hydrochloric acid. Hold on. Hold on, I didn't mean to do that. We got to figure that out. All right. So just a little review. What's that starting reagent called? Fe2S3. What would its name be?
Iron sulfide.
Close. The words are iron sulfide, but what's missing?
Iron 3 sulfide.
Yeah, it's iron 3 sulfide, because iron's one of the ones that can have multiple different charges. Sulfide has a 2- charge, so if you've got 3 2- sulfides, you need 2 3+ irons to balance that out, so that's iron 3 sulfide. So iron 3 sulfide and hydrochloric acid forms iron 3 chloride and hydrogen sulfide. Dihydrogen sulfide is another way that you could say that. An interesting thing about that HCl, we think of HCl as hydrochloric acid because that's usually how we use it. But actually, HCl pure is a gas, hydrogen chloride gas. It's only when you dissolve it in water that it becomes hydrochloric acid. So when you see HCl with the little AQ, that tells you it's hydrochloric acid. If it's HCl with a little G, then it's hydrogen chloride, the gas. It's not an acid. So anyway, first we have to figure out if this equation is balanced or not. Any idea? You can probably see if you looked at it, but what I always recommend is do what I call an atom inventory. Just count up how many of each type of atom you have on each side and see if they match up. So on this side, we've got 2 Fe's, we've got 3 S's, an H, and a Cl. Everybody see where I got those numbers from? Okay. So then on the other side, we've got 1 Fe, 1 S. I'm going to keep them in the same order so I can compare easily. And 3 Cl. Is that in balance? Don't think so, right? Everything is screwed up. Everything either loses or gains atoms, and we know that that can't be right. They have to have the same number of each type of atom on each side of the equation. So let's bring them into balance. Remember, the way that we bring them into balance is by putting a number out front, which is called the coefficient, telling us how many of that molecule are reacting in this ratio. So let's start with the iron. It doesn't really matter where you start. How would we bring the irons into balance? How would we bring Fe into balance? What kind of number can we put out in front of one of the molecules?
2
Where?
on that side. On the right side.
Yeah, we'd put a 2 out in front here. All right. And now this is an important part. You have to correct your inventory, because when you put that 2 out in front, you don't just affect the iron, you're also affecting other stuff. You're affecting the chlorine in this case too. So we've got to, do you have a question? Okay. So that changes to 2. And then instead of 3 chlorine, we now have 6. Because we have 2 of those whole units and each unit has 3. All right. Since we just changed the chlorine, let's go with that one now. We got 6 on the right and 1 on the left. How do we bring those into balance?
We need to write 6 part of H5
Yeah, we're going to put a 6 here, right?
and 3 in part of H2.
All right, hold on. You're ahead of me a second. Let's go step by step here. So that's going to give you 6 of these and 6 of those. That little part where I correct the numbers, that's really important, and that's a common error here, is you get so excited about balancing one of the atoms that you forget that you also mess with the other one, and then you try to bring those into balance and it doesn't quite work out. So make sure you always correct to the newest numbers. Okay, so now we're getting closer. Irons are in balance, chloride's in balance, hydrogen is not, and sulfur is not. So let's balance out our hydrogens. We've got 6 on the left and 2 on the right. How are we going to get 6 on the right? Yeah, we'll need 3 here, and that gives us 6 hydrogen here and 3 sulfur, and now it's balanced. So that actually took care of the sulfur too. So now we would say we have a balanced chemical equation for this process. All right, you try one. This is a molecule called butane, C4H10. It's a hydrocarbon. It's volatile. It's what's in lighters, the fuel in lighters. When butane burns, it reacts with oxygen. So this is butane gas and oxygen gas. And it forms carbon dioxide gas and water vapor. All right. Now, a couple of things I'm going to caution you about with this one. One thing you see in this reaction that you didn't see before is that oxygen appears in 2 different molecules on the same side. You see that? You've got oxygens here and you've got oxygens over there. If you encounter an equation where you have multiple of the same atom, or the same atom and multiple molecules on the same side, leave that till last. Otherwise, it's too hard to balance it. You don't know which place to put the number, so leave that till last. Other than that, go ahead. You can do it the same way we did the previous one. You will probably run into a problem. See if you can solve that problem when you run into it. So set up your atom inventory and start going atom by atom to figure out how you need to balance it. Anybody run into this problem yet? Or something doesn't seem to quite work? Keep working on it. I'm going to set it up here too. So anybody get to this point? I brought my carbons into balance, and I brought the hydrogens into balance. And each time I did that, I also messed with the oxygens. But now I have a situation where they've got 13 oxygens on the right and 2 on the left, but I can only change the left in terms of 2. So there's no way I can have some number times 2 and get to 13, right? So what do you do if you end up with this issue where you can only change things in even numbers on the left, but I've got an odd number on the right? How could I possibly work this out? Anybody come up with a solution to that?
Multiply.
Yeah, go ahead.
Put everywhere, multiply everywhere by 2.
Yeah.
Put 2 before the carbon for each 10.
Right.
And then just match.
And redo it, yeah. Yeah, that's exactly right. So if you run into this problem, because this comes up a lot in different equations, where you can only have even numbers on the left and you have odd numbers on the right, or you can only have odd numbers on the left and even numbers on the right, you multiply everything by 2. The odd numbers go away, because any odd number times 2 is an even number. So we can, instead of this, we'll go 2, and instead of 4, 8, and instead of 5, 10. So now we can recalculate and make sure we've got everything. So this should be doubled. This should be doubled. We're waiting on the oxygen because that's the one that's the problem in the first place. That gets doubled. This gets doubled. And now instead of 13 O's, we have 16 plus 10, which is 26. So that we can deal with because 13 times 2 is 26. And now we've balanced that. So I'll erase this so it's a little clearer. So balancing equations also has a bit of trial and error involved. Sometimes you kind of go through it and you realize, well, that's not going to work. So then you have to double something or you have to change something else and then try it out again and see if that works. Pencils are definitely your friend when you're balancing equations because you will go back and forth and have to try some different things. You won't always just be able to work through it and get the answer right away. All right, let's try another one. Oh, I didn't put the states here. This should be aqueous, aqueous. Something like that. All right, let's review our names again. What's Na3PO4? Sodium phosphate, good. MgCl2? Magnesium chloride. Mg3PO42? Magnesium phosphate. And NaCl? All right, good, good. Keep working on those because ultimately what we're going to do is instead of writing out an equation, I'm just going to tell you sodium phosphate reacts with magnesium chloride and forms this, and you have to write down those formulas. And as you could see, if you don't write down the formulas right, they're not going to balance right either. So make sure you go back and keep reviewing those names if you haven't, if you don't feel good about that yet. All right, see if you can get this one balanced. That maybe it was like your work phone and like
He's out of country, so I had to do it.
How are these going? How's this one going? Did anybody come up with a little shortcut for this one? It's not necessary. You can do it the regular way. But one thing you might look at is in this reaction, the phosphate ion doesn't change. It's a phosphate ion on the left. It's a phosphate ion on the right. So instead of separating it into P and O, you can just keep it together as phosphate and balance it as phosphate ions. That's especially useful in problems where there's multiple ions that have oxygen in them. So if you could imagine if there were like phosphate and sulfate, if you tried to balance the P, the S, and the O's would be in everything, and it might be a lot more complicated to deal with. So when I do this inventory, I would do like 3 NAs, 1 PO4, 1 Mg, and 2 Cls. But you could also do it 1 P and 4 Os. It'll still work, still be totally fine. I find that if you can keep the ions together, if you know they don't change, it's just going to save you a step, or maybe a couple steps, depending on the equation. So on this side, we've got 1 Na, and now we can have 2 PO4s. Now, if we broke that down all the way, we'd say 2P and then 8O, because the 2 applies to all 4 of those oxygens in the phosphate. So then we've got 3 magnesium and 1 chloride, obviously out of balance. So did anybody come up with the numbers for this one? What'd you get? If you just read across from left to right here. 2 and 3
then nothing,
and nothing
and then 6.
and 6. What do you think? Is that what you got? All right, let's check it. Now we've got 6 NAs, 2 PO4, 3 Mg, and 6 Cls. And on this side, we've got 6 sodium, 2 of those, 3 of these, and 6 Cls. Look good. It's another nice thing about these types of problems. If you're doing a quiz or a test or something, you always know if you're right or not. You just count up the atoms, And if the atoms match up, you're right. If they don't match up, it's not balanced yet. So as long as you can count atoms, you'll always know if you've got a balance right or not.
What was the biggest digit in front of them? Like we have here 13, so can it be like,
Yeah.
can it be a big one?
Could be whatever. Now, if sometimes you'll find in some of these that take a little bit of trial and error and bouncing back and forth, sometimes you'll find that you end up with really big numbers that all have a common factor. So let's say we did some back and forth here and we came up with 4, 6, 2, and 12. Kind of like multiplying this whole thing by 2. For me, that's still a balanced reaction or a balanced equation. That's fine. All the math stuff that we're going to do with these balanced equations, that'll still work. It's not a big deal. Technically, you always want to balance to the lowest possible numbers, so you would divide everything by 2. But I wouldn't mark it wrong if it's a multiple. But yeah, the numbers can get really big. That also said, if you're doing one of these problems where you have written down the formulas yourself, and you start to see that like something is just not balancing, and you just keep getting bigger and bigger and bigger and bigger and bigger, and you just can't seem to get it balanced, chances are one of your formulas is wrong. Maybe you just copied it down wrong, or maybe you wrote the formula wrong, something like that. If it seems to just not be possible to balance, chances are one of your formulas is wrong.
We're going to have a test, like for formula on both sides.
Yes.
Okay.
Yeah. Well, or I'll give you the names. Yeah.
Okay, because we have at school, like we had just first one, then we had.
Oh, I'm sorry. Yes, we're gonna do that too.
No.
Yeah. We're gonna do a type of it. So that's a good question because it kind of brings us into the next part of it, which is ultimately the point of doing all these reactions, or part of the point of it is how do we actually control it? How do we predict what we want to make? That's really what you want to do in chemistry. You want to say, I want this stuff. How do I make that stuff? Well, I take some of this and some of this, and I make that. That's what we're going to look at next. Now, there's so much in chemistry that affects this. There's all different kinds of molecules, all different kinds of reactions. You know, you can go on, of course, and study your whole life in chemistry and still only know a small fraction of those possibilities. When we're still finding new ones, you know, every day. But there are a few categories of reactions that are very predictable and that tend to produce the same types of products. So that's what we're going to look at next, are these types of reactions. You're going to actually do each type of these reactions in lab on Tuesday, and then those will be the types of reactions that I would ask you to predict on an exam. So we're going to look at categories of reactions or types of reactions. Now, this is not an exhaustive list, but the reactions we see will nicely fall into one of these categories. We're going to look at 3, 4 or 5-ish. We won't get through all of them today, but first type is going to be called combination or composition. Well, you're not the only one. Yeah. That was actually strangely appropriate. So combination, these are pretty easy. You take 2 reagents and you combine them together. So 2 things, and then you just stick them together. Example of that is let's look at a couple examples of it. The one we're going to do on Tuesday is burning magnesium metal and oxygen. The magnesium reacts with the oxygen and makes magnesium oxide. Now notice when we stick these together, we have to build a new compound. So we take magnesium and we take oxygen and we put them together to make a compound from magnesium and oxygen, but we don't just stick the Mg and the O2 next to each other. It's not that simple. We have to build a new compound and say, okay, magnesium ions are +2, we know that from the periodic table. Oxide ions are -2, we know that. So we're going to need 1 magnesium and 1 oxide to form our compound. All right, so you still have to build these compounds just like we did a couple chapters ago. Is this a balanced equation then? It's not. So we have to balance it. The balanced equation looks like that. So that's an example of a combination reaction. Our water synthesis is another example of that. And there are a couple other examples in the book. But basically, you take all the stuff on the left, you put it together into a new compound, and sometimes that will be predictable, and sometimes it'll be hard to predict. But that's the general idea. All right, second category. It's kind of the opposite. Decomposition. Decomposition, you have some reactant, AB, and it decomposes into separate products, A and B, or A, B, C, or D, however. These are often pretty much impossible to predict. Because if you're only given one reagent, how do you really know what it's going to break up into? Is this part going to go over here? Is this part going to go over here? So often this is really difficult to predict. Some examples are the one we're going to do in lab on Tuesday, which is calcium carbonate decomposes into calcium oxide and carbon dioxide when it's heated. So you see how that kind of splits off? Now, how would you know that it decomposes into CaO and CO2 and not CaO2 or CaO and CO or Ca and CO3 or something? You know, we don't really. So that these tend not to be really predictable in terms of this class, in terms of what I would ask you to be able to predict, just because there's so many different possibilities of what could happen in that decomposition. So then let's move on to the third category, kind of third and fourth, we'll say, which is replacement reactions. And these we can usually predict. There's two types of replacement reactions, single replacement and double replacement. And this is a big category of reactions, so that they're pretty nice usually in terms of being able to predict them. Our first category will be single replacement. And that looks like this. You have one kind of thing by itself, an atom, an element, and then you have a compound, BC, and they switch places. One of them comes out and becomes an element on its own, and the other one goes with whatever was there before. Some examples of this. Zinc metal can react with hydrochloric acid to form zinc chloride and hydrogen gas. This is not balanced, so we have to do that. So notice how the zinc is by itself and the H is with the Cl. Then the zinc goes with the Cl and the H goes off by itself. So that's what we would call single replacement. And then the other part, and we're going to do that one too.
Can we have A, B, and C going to be separately, or?
Sure, it just depends on how you define them. So usually we have to use, and it's not always going to work, but let me give you another example before we go on here so we can see if we can figure this out. Chlorine gas reacts with potassium bromide. Oh, solid potassium bromide, sorry. All right, so we're trying to figure out what the products are. And the thought process here is, well, we can first see that it's a single replacement because it's got one thing by itself and then two things together. So we'll say, all right, good guess, this is a single replacement. So now the question is going to be, is the CL going to go with the BR or is the CL going to go with the K? What do you think? Yeah, everybody said K. You're all right. Why? How'd you know? Because what? It's metal. Yeah. So we kind of, even though you haven't been in chemistry class for that long, you got some intuition about this sort of thing, right? You think like KCl, that seems like something that's a thing. CLBr, I don't know about. And actually, CLBr is also a thing. But having that metal, non-metal, that KCl, kind of like KBr, those kinds of compounds that we've seen a bunch of, those are more common. So that would be a better prediction. And remember, these are predictions. You sometimes have to take a little bit of a guess. And you have to ask yourself what seems more likely to happen here. And so you're right. What is more likely to happen is that the K will go with the Cl and form potassium chloride. And the bromine gas will be off by itself. And that is also not balanced. So we have to do that. All right, and then the next part of this category is the double replacement. This is where you have usually two ionic compounds, A, B, and C, D, and they switch partners. So you have cation, anion, cation, anion. The cations take the other anions. Let's look at some examples of that. The trickiest thing with this part, with this one, this is actually the easiest one to predict because you know what the cations are, you know what the anions are, and you just switch places. The only tricky part is you have to build new compounds based on the ratios. So let's look at, well, here. Let's see if we can just figure this one out. What's BaCl2? Barium chloride, right? So here's barium chloride, and what is the next compound called? Sodium sulfate, right? Barium chloride and sodium sulfate. So can you pick out the A, B, and the C, D? Yeah, our cations are barium and sodium, and the anions are chloride and sulfate. So they're going to switch places. The chloride's going to go with the sodium, and the barium's going to go with the sulfate. But we have to build new compounds based on the charges of those ions. So we can say these two are going to go together, but they're not going to form Na2Cl2, right? What are they going to form? NaCl. And then these two are going to go together. And what's the charge on barium? +2. And what's the charge on sulfate? Yeah, also +2. So those, or -2. Yeah, it's -2. So those will go together. And the thing that causes these reactions to happen is usually the formation of a precipitate.
Can we switch first body SH2 and then SO4 and then?
Yeah, it doesn't matter which order you write them on. Somebody said NaCl first, so I wrote that one first. It doesn't matter. How you know whether or not a precipitate is formed is a different question that we'll get into later. But what I want you to be able to do from these is to recognize this double replacement reaction. We'll recognize what type of reaction any reaction is, and then draw the product based on that. So let's try one. Yeah, this is not balanced, so let's do that first. Okay. One second. Lost my place here. Okay, for our last one, I'm going to ask you to pick the product and balance the equation. Not AL2. So first we identify this as a double replacement reaction because it's made up of two ionic compounds, plus minus plus minus. So you got to swap the ions, build new compounds, and then balance the equation. So we can do that. The trickiest part is making sure that these charges balance up. So let's review that. What's the charge on aluminum here? It's +3. And what about sulfate? -2. The potassium is?
1.
+1, and hydroxide is?
-1.
-1. The other nice thing about these reactions is if you forgot one, like you forgot the charge on OH, you could say, oh, I know potassium's +1, KOH is neutral, so OH must be -1 to balance it out. Or if you didn't know aluminum, but you knew sulfate from that list, you could calculate that aluminum needs to be +3. All right, anybody got some products for this one? Got some products? All right, what's one of the products? What's it called? Let's do it by name. Potassium sulfate, yeah. That's another clue with some of these. If you can name them, you can just switch the names, come up with the new compounds and do it that way. So we've got aluminum sulfate and potassium hydroxide. That's going to become potassium sulfate and aluminum hydroxide. So we've got potassium sulfate, which is K2SO4. And we've got aluminum hydroxide, which is AlOH3. Aluminum's still +3, so we need 3 OHs to offset it. And that is a solid precipitate. Now, whether you know if something is aqueous or solid, that's not something I would expect you to predict. We might get into that later about what types of things are soluble and what types of things are not soluble, but I would not expect you to predict that. But I would expect you to be able to write down K2SO4 and AlOH3 based on knowing those charges and building those ions. So is this balanced? How do you balance it?
6 before 3,
So we need 6 of these,
then 3,
and 3 of these,
and then
and 2 of those. Yep, looks good. What?
How do you get K2?
K2, good question. So you know that the potassium has to go with the sulfate. So you have to think potassium is a +1 ion, sulfate is a -2 ion. So I need 2 +1s to go with the -2. Okay, so you have to, the way I think about it is you have to build a new compound. Like you figure out that the potassium goes with the sulfate, but you have to then build that out to figure out how many of each you need to have a neutral compound. As always, the goal is to have a neutral compound overall. So part of that is knowing the charges from the stuff we did in the last chapter and then being able to put those back together again. All right, so that is it. Quiz Tuesday and Lab Tuesday.
I wouldn't have it.
Quiz will pretty much be everything since the last quiz. So a lot of the naming, the polarity stuff, what are stuff is polar, and electronegativity, and then chemical equations.
I'm gonna have it that.
The what?
That bonding. Those factors.
Yes, but just a little bit that we talked about.
What is it again? Naming, polarity, electronegativity.
Yeah, molecular compounds and chemical equations. I'll leave off the mole calculations on this quiz because we will get into that more later.